Right, hello, Dr. Russell. Today I'm going to be talking about CRISPR, also known as clustered, regularly interspaced, short palindromic repeats. And in this presentation, I'm going to be putting a little more focus on Cas9, which is the most popular Cas protein that is used a lot for genome editing. And of course, this is Chemistry 223, spring term 2020 here at Mountain Community College. So first, a little bit of history and some background. CRISPR genes were first discovered in 1987 by Yoshizumi Ishino in the E. coli genome at a Japanese university. Fast forward to 2012 is when the Cas9 Cas protein was discovered by Emmanuel Charpentier and Jennifer Doudna, which won both of them the Nobel Peace Prize. In this picture right here, on the far right, we have Jennifer Doudna, and in the center, we have Emmanuel Charpentier. And then on the left, we have Feng Zhang. There's a lot of controversy in the science community on who actually discovered and put into place the Cas9 protein. Of course, as we now know, Feng Zhang does hold a lot of the key patents, but many people in the community, as well as a lot of recognition and awards, were given to Jennifer Doudna and Emmanuel Charpentier for the discovery. So how does it work? The first part of understanding is knowing what CRISPR stands for. And as I mentioned, it's clustered, regularly interspaced, short palindromic repeats. So they're different from normal genes because they contain nucleotide repeats in spacers, which you can see on the graph in front of us. This meaning that they're interspaced identical nucleotides separated by spacers in the CRISPR gene. And there's a third part to knowing what it is, and that's CRISPR-associated genes, also known as Cas or CAS. Cas genes are made up of helicases and nucleases, which are proteins that unwind and cut genes, which led us to believing that we can use Cas genes to cut, unwind, and in the future, edit different genomes. Now, Cas genes create what we call Cas proteins, and that's what Cas9 is. Cas9 is a protein that is mainly used for snipping and the editing of the genome, which is the leading use, of course. Now, Cas proteins work together with the spacer DNA interspaced between the nucleotides to create what are called cRRNA or CRISPR RNA, to help fight off certain bacteriophages such as E. coli, which you can see on this graph ahead of us. Actually, I'm going to go right back. Now, the next part to understanding CRISPR is, of course, Cas9, which the scientific name is Streptococcus pyogenes, which Cas9 is technically an enzyme which is used in the CRISPR process, and as I mentioned, acts as the hypothetical scissors and contains all the pieces to be able to cut out the DNA and then edit the DNA. Although you may be wondering, how does it cut out the DNA and where does it know where to cut? And that's where PAMs come in, or PAMs. Those are also known as protospacer adjacent motifs. And they serve as the tags, and they sit adjacent to the target DNA sequence that they want to have cut, and then they want to have edited and placed with new DNA inside. So then we go on to uses. And the uses of CRISPR and Cas9 DNA is highly extensive. It can be used anywhere from making tomatoes spicy, as you see on the picture to the left, because peppers and tomatoes millions of years ago had a common ancestor, which is why we can use CRISPR to edit the gene of tomatoes and make them spicy, similar to their past common ancestor. It can range from that in the food industry all the way to de-extinction and bring back the woolly mammoth. It really ranges, and that's why we must be careful and mindful of the things we use CRISPR for, and that's why CRISPR is such an amazing discovery, because of the far extent of what it can be used for. It's not just used for medicine, it can be used for different industries, like I mentioned. So then, because of all this power behind CRISPR, there's a lot of controversy created. As I mentioned, of course, there was the controversy of who actually discovered Cas9, which of course was the most popular Cas gene or Cas protein. And then it's, when does using CRISPR overstep the lines of what is morally and ethically correct and what is not? Of course, many people would say, yes, it would be beneficial to bring back different extinct species, but then there's many people that would say it's not. And it all boils down once again to what is morally correct, what is ethically correct, what do we actually need rather than what do we actually want, and what will help benefit humans in the future and what won't. Which brings it down to morals. Are we so-called playing God, as people would say? With CRISPR, we have so much power now to be able to change so much because we now have the power to change the blueprint of almost every living species. So when does it hit the point where, rather than using CRISPR to help benefit humans and benefit the world, are we using it to just change what we want? Like, is it morally correct for me to use CRISPR and edit my DNA to where I have different colored eyes? It all comes down to morals. So now it's about the future of CRISPR. How do we stay mindful? How do we use it in an equitable sense? We need to be very careful of the changes we make now because we may never know what those changes can bring in the future. And of course, it's very hard to predict. That is why in the scientific field, we need to take things step by step, be careful with how we use it and what we do with it. Of course, CRISPR is still at its early stages, and all these things won't be happening overnight. The woolly mammoth won't be all of a sudden appear tomorrow. Jurassic Park won't be opening tomorrow. But of course, we need to stay mindful and prevent future issues. Thank you.